everyone. In this video, let us discuss about long short-term memory, which is in short called as LSTM, right? So LSTM is an advanced RNN. So it is an advanced recurrent neural network, a sequential network that allows information to persist. So what we have seen in RNN is like it has some limitation or some problem on vanishing gradient, right? So this is what we have seen. Vanishing gradient problem it has got. So in long short-term memory, it is capable of handling the vanishing gradient problem. So a recurrent neural network is used for persistent memory. Say, for example, you are looking into some video, you are watching a movie. So you may remember the previous scene, right? Or else just think that you are reading a book, but you remember the terms that you have studied in the earlier chapter, right? So accordingly, RNNs work. They remember the previous information and use it for processing the current input, right? But the shortcoming of RNN is that they can remember long-term dependencies due to vanishing gradient. So LSTMs are explicitly designed to avoid long-term dependency problem, right? So let us try to understand what long short-term memory is, right? So it is usually just called as LSTMs. It is a special kind of RNN capable of learning long-term dependency. So they work tremendously well on a large variety of problems and it is being widely used, right? So it is explicitly to avoid the long-term dependency problem. So remembering information for a long period of time is practically their default behavior, not something they struggle to learn. Okay. So now look at this. Let us discuss about the LSTM architecture. So at high level, LSTM also works something similar to RNN cell. Here, it is the internal functioning of the LSTM network, right? So the LSTM consists of three parts. You can see 1, 2, and 3. The LSTM consists of three parts, and each part shows an individual function. So the first part chooses whether the information coming from the previous timestamp is to be remembered or is irrelevant. So what this do is it will choose whether the information from the previous timestamp is to be remembered or is irrelevant and can be forgotten, right? So in the second part, the cell tries to learn new information. So in the second part, what you can see is it can, right? So it can try to, 1 minute. Okay, fine. So it will try to add a new information, right? So the third one is that there is a third part that is basically the output gate, right? So this is basically the output. So here what will happen is the cell passes the update information from the current timestamp to the next timestamp, right? So hope this is clear, right? So the part 1, forget irrelevant information. Part 2, add or update new information. Part 3, pass and updated information, right? Fine. So let me tell you, these three parts, we call it as gates. The first part, we call it as forget gate, right? We call it as forget gate. And the second part is known as the input gate. And the last one is called as the output gate. So like simple RNN, LSTM also has some hidden state. So that LSTM also has a hidden state where HT minus 1. So it represents the hidden state of the previous timestamp and HT is the hidden state of the current timestamp, right? So in addition to that, LSTM also have a cell state that is represented as CT minus 1 CT. So just remember, so LSTM also have hidden state for the previous timestamp and the current timestamp, and also it has cell state for previous as well as the current timestamp. Okay, so now look at this, right? So here you can see that long-term memory CT minus 1, HT minus 1, CT and HT. This is what I was telling, right? So you can see here HT minus 1 hidden state of previous timestamp and this HT is basically for the current stamp, and this is for cell, right? So the cell state basically carries the information along with the timestamps. Okay. So here the hidden stamp is basically known as short-term memory, and the cell is called a cell state is known as long-term memory. So this hidden state, no, HT minus 1, HT, the hidden states are called as short-term memory, and the cell states are called as long-term memory, right? So the cell state carries the information along with the timestamp, right? So let us try to understand how this basically works, right? So this is what we have to understand. So let me write some example. So Alex is a good person, right? So this is one sentence, and also I'm adding with that like okay, Harry on the other hand is evil. Okay, so it is the sentence, right? So let us try to understand how this sentence basically works. So we have two sentences here separated by a full stop, right? So the first sentence says that Alex is a nice person, and the second sentence is that Harry on the other hand is evil. So it's very clear that in the first sentence, we are talking about Alex, and in the second step, we are talking about Harry. So as we move from the first sentence to the second sentence, our network should realize that there are no more talking about Alex, right? Because now our subject is basically Harry, right? So here, the forget gate of the networks allows it to forget about it. Hope I'm clear, right? So this is what we have to understand about the forget gate. So in the cell of the LSTM network, the first step is to decide whether we should keep the information from the previous timestamp or forget it. Whether we should keep the information or we have to forget it, right? So this is basically the equation of the forget gate, right? So Ft is equal to sigma xt into Uf plus Ht minus 1 into Wf, right? So what is this xt? Xt is nothing but input to, this is t, right? So input to current timestamp, right? So current timestamp. So what is this Uf? Uf is nothing but weight associated with that, associated with the input, right? So what is Ht minus 1? So again, this is going to be the hidden state, right? T minus 1, right? So hidden state of the previous timestamp, right? Hidden state of the previous timestamp, right? So what is this Wf going to be? This is the weight matrix, right? So what is Wf? This is the weight matrix associated with the hidden state, right? So now I hope this is clear, right? So what does this forget gate do? It decide whether we should keep the information from the previous timestamp or forget it, right? So then the sigmoid function is applied on it. Now we know about sigmoid, right? So what does this sigmoid function basically do? It will fit a number between 0 to 1, right? So already we got Ft, right? In forget gate, we are getting output as Ft, right? So now this Ft is being multiplied with the cell state of the previous timestamp. So we got Ft. This is being multiplied with the cell state of the previous timestamp, right? So we get Ct minus 1 into Ft, right? So like this is what we are getting. If this is equal to 0, if Ft is equal to 0, forget everything. And if it is equal to Ct minus 1, if Ft is equal to 1, forget nothing, right? So if Ft is 0, then the network will forget everything. And if the value of Ft is 1, it will forget nothing. So the first sentence we were talking about Alex, and after a full stop, the network will encounter Harry. In an ideal case, the network should forget about Alex, right? So the next one, right? So the next one is about the input gate, right? So let us look into the input gate now. Okay. So now let me write another example like Alex knows swimming. He told me over the phone that he served the Navy for 3 long years. Okay, so let us try to understand. So in both these sentences, we are talking about Alex. So both give different kind of information. So the first sentence is telling me that he knows swimming. And in the second sentence, it is saying that like he served the Navy for 3 long years, right? So both give different kinds of information about Alex. So in the first sentence, we get the information about swimming. Second sentence, over the phone, we got to know that he served in the Navy for 4 years. So now just think about it. Based upon the context in the given first sentence, which information of the second sentence is critical? So first, he used the phone to tell or he served in Navy, right? So in this context, it doesn't matter whether he used the phone or any other medium of communication to pass on the information. So the fact that he was in the Navy is important information and is something we want our model to remember. So this is the task of the input gate. So input gate is used to quantify the importance of the new information carried by the input. So this is the equation of the input gate. IT is equal to sigma xt into ui plus ht minus 1 into wi. So what is this xt? Xt is nothing but the input at the current timestamp, right? Fine. So what is ui? Ui is nothing but weight matrix of input, right? So what is ht minus 1? We know that it is a hidden state at the previous timestamp. So what is this wi? Wi is the weight matrix of input associated with the hidden state. So again, we have applied sigmoid function over it. So as the result of that, the value will be ranging from 0 to 1, right? So now the next one is about the new information, right? So now here, like what is being done is, see, Ni is equal to tan H, right, xt into uc plus ht minus 1 into wc, right, wc, right? So now the new information needed to be passed to the cell state is a function of hidden state at the previous timestamp, that is t minus 1, and input x at timestamp t. So what is the activation function here? Activation function here is tan h. So what is happening now? Because of the tan h function, we will be getting the information ranging from -1 and 1. So if the value of nt is negative, right? So sorry, this is basically nt, right? So if the value of nt is negative, then the information is subtracted from the cell state. And if the value is positive, the information is added to the cell. Very simple. See, nt is negative, the information is subtracted from the cell state. If the value is positive, then the information is added to the cell state at the current timestamp, right? So the nt won't be added directly to the cell state, right? So you can, this is what previously I have written over there, and this is being, the cell date now being updated. So what is happening now? Ct is equal to ft into ct minus 1 plus it into nt. So what is ct minus 1? Ct minus 1 is the cell state, right? It is the cell state at the current timestamp, sorry, and others are the values we have calculated previously. Sorry, I'm talking about CT. CT is the cell state, right? So hope it is clear. Now the next one is about the output. Now let me give you another sentence. So this is happening here, updating the cell state, right? Okay. So now let me tell you another one, right? So Alex single-handedly fought the enemy and died for his country, right? For his contributions, brave, right? So during this task, we have to complete the second sentence, right? So we have to complete this sentence basically. So now the minute we see the word brave, we know that we are talking about that person, Alex. So in the sentence, only Alex is brave. We cannot say that enemy is brave or the country is brave. So based on the current expectation, we have to give a relevant word to fill in the blank. So that word is our output, and this is the function of our output gate, right? So this is the equation of the output gate. Its value also lies between 0 and 1 because this is also a sigmoid function. Now to calculate the current hidden state, we will use OT and a tan H of the updated cell state, right? OT and tan H of the updated cell state. So what do we get now? It turns out the hidden state is a function of, so what do we get over here is, it is a function of long-term memory, right? So we get it as a function of long-term memory and the current output, right? And the current output. So if you need to take the output of the current timestamp, just apply the softmax activation function on it. So now here, the token with the maximum score in the output is the prediction, right? So this is how it looks like, right? So this is how it looks like. So you can look at the picture like, so you can see that, there is A and there is here A again. So this is the activation function you can see over here. Okay.
The LSTM networks in detail. So we have a clear understanding about recurrent neural networks, right? So what we have come across recurrent neural network, just let me give a recap of it. See, for example, like we are trying to, or we are watching a movie, and whenever you watch a movie, you will be remembering the last scenes, right? So what has happened actually before, right? So recurrent neural network is something related to that, right? So now what is the major problem that we faced in RNN is about the long-term dependencies, because they might be able to connect previous information to the present task, such as previous video frames might inform the understanding of the current frame. If RNNs could do this, they would be extremely useful, but can they? Right? So it depends, right? So sometimes we only need to look recent information to perform the present task. So for example, consider a language model trying to predict the next word based on the previous one. So if you are trying to predict the last word in a sentence, we don't need further context, right? So it is pretty obvious the next word, what it is going to be. So in such cases where the gap between relevant information and the place that it's needed is small, so RNNs can learn to use the past information. But there are also cases where we need more context, right? Where we need more context. So consider a statement, right? I like to, something like that, right? So I like, otherwise I like, and then I'm writing, I'm not writing anything, right? So, or I am writing like I speak fluent. So it could be English, it could be Spanish, it could be French, right? So the recent information suggests that. So let me make it very clear. No, like I lived in India. So I'm writing I speak, right? I speak fluently in, right? So now this could be, when we say India, it could be of any languages, or more specifically could be Hindi, right? So recent information suggests that the next word is probably the name of a language. There is no doubt about it. It is going to be about the name of a language, right? But if we want to narrow down which language we need the context of Hindi from further back, right? So it is entirely possible for the gap between the relevant information and the point where it is needed to become very large. So when the gap grows, RNNs become unable to learn to connect the information. So RNNs are absolutely capable of handling such long-term dependencies. A human could carefully pick parameters for them to solve toy problems of this form, right? So in practice, RNNs don't seem to be able to learn them, right? So let us try to understand this LSTM, long short-term memory networks, right? Usually called as LSTMs. These are also special kind of, this is also a special kind of RNN, which is capable of learning long-term dependencies. So it is being very popular right now. It is explicitly designed to avoid the long-term dependency problem, right? So remembering information for long period of time is practically their default behavior, not something they struggle to learn, right? So all recurrent neural network have the form of chain of repeating modules of neural network. So in standard RNNs, the repeating module will have a very simple structure. Like we have seen, like it has only tanh layer, right? But LSTMs also have chain-like structure, but the repeating module has a different structure, right? So the repeating module has a different structure. Instead of having a single neural network layer, there are actually 4 interacting a very special way, right? So we are not going to dive deep right now. So in this diagram, we will try to look everything step by step, right? So that is what we are going to do now, right? So the key, look at this one. Now let us compare this and this, right? So you can understand the difference, right? So this is basically the RNN. We had only the tanh layer, but here you could see the 3 sigmas are there and 1 tanh is there, right? So this is what we can understand, right? So here we can see that each line carries an entire vector from the output of one node to the input of others. So here you can see a pink circle, right? So this represents point-wise operations like vector addition, and the yellow box represent what is that, a network, right? Network layers. Lines merging denote concatenation. So you can see this is basically the vector transfer. This is the concatenation, and a line forking denote this is being copied, and the copies are going to different locations. So the key to LSTM is the cell state, right? Cell state, the horizontal line passing, running through the top of the diagram, right? So that is what we have seen, right? I'll be showing you. So this is the cell state. This is the cell state, right? Fine. So the cell state is like a conveyor belt, right? It runs down the entire chain, right? So with only some minor linear interaction. So it is very easy for information to just flow along it unchanged, right? So the LSTM does not have the ability to remove or add information to the cell state. It is being carefully regulated by structures called gates. Okay, so the gates are a way to optionally let information around. So they are composed out of sigmoid neural net layer. That is what we have seen, right? That is what we have seen, and a pointwise multiplication operation. So the sigmoid layer, what it does, it outputs number between 0 and 1 and describing how much of each component should be let through. So value of 0 means let nothing through, right? While a value of 1 means let everything through. So an LSTM has 3 of these gates to protect and control the cell state, right? So you can see the 3 states over here, right? So now the first step in our LSTM is to decide what information we are going to throw away from the cell state. So this decision is made by the who will be taking this decision? Basically, this will be taken by the sigmoid layer, right? So called the forget gate layer, right? So this decision is made by sigmoid layer, which is called as the forget gate layer. it looks like HT minus 1 and XT, and it outputs a number between 0 and 1, right? 0 and 1 for each number in the cell state, CT minus 1, right? CT minus 1. So here, like in case if you get 1, we can say that completely keep this. Or if you get 0, we may try to completely get rid of this, right? So the example, you can take a language model which is trying to predict the next word based upon the previous one. So in such problem, the cell state might include the gender of the present object, so that the correct pronouns can be used. You got my point, right? So the gender must be mentioned so that everywhere, say for example, if it is a man, everywhere it is being written like he, his, him, something like that, right? So this is what I am trying to say now, right? So when we see a new object, we want to forget the gender of the old object, right? So now this is mentioning about a man. After that, it is mentioning about a woman. So now it has to forget that man character basically. So the next step is to decide what new information we are going to store in the cell data, right? So now here there will be two parts. What are the two parts? First, there will be a sigmoid layer. First, there will be a sigmoid layer, right, called the input gate layer. It decides which values we will update. Next, a tanh layer, which creates a vector of new candidate value CT, right? So that could be added to the state. So in the next step, what we will do, we will combine these two to create an update state. So you can see over here, you can see sigma as well as tanh. So sigma, in the sense, you can see that HT minus 1 and XT, right? And for tanh, you can see that again HT minus 1 comma XT, right? So you can see that WI, WC are varying, right? So now what is happening over here? Right? So now what is happening over here? See, we have done that. Now it is now time to update the old cell state, that is CT minus 1 into the new cell state CT, right? So the previous steps already decided what to do. We just need to actually do it, right? So we have to multiply the old state by FT, forgetting the things we decided to forget earlier, right? So we decided to forget earlier. Then we add IT into CT. This is a new candidate value scaled by how much we decided to update each state value. So in the case of the language model, this is where we would actually drop the information about the old subject gender, and we can add the new information as we decided in the previous step. So finally, we need to decide what we are going to output. So this output will be based on our cell date, but will be a filtered version. So first we run a sigmoid layer, which decides what part of the cell date we are going to output. Then we put the cell state through tanh to push through the, then we are passing it to the tanh, right? To push the values to be between minus 1 and 1 and multiply with the output of the sigmoid gate, so that we can only output the paths we decided to. So for the language model example, since it just saw an object, it might want to output information relevant to a verb in case that is what is coming next. So for example, it might output whether the subject is singular or plural, so that we know what form of a verb should be conjugated into if that's what follows next, right? So what are the variants on long short-term memory? Like we have seen before is just long short-term memory, but not all LSTMs are the same as the above. In fact, it seems like every paper involving LSTMs uses a slightly different version. So the differences are minor, right? So one popular LSTM is adding a peephole connection. So this means that we let the gate layers look at the cell state, right? So you can see over here, right? So here you can see the peepholes over here to all the peepholes over there to all the gates, right? And instead of separately deciding what to forget, what we should add new information to, we make those decisions together. So we only forget when we are going to input something in its place, right? So we only input new values to the state when we forget something older, right? So here a slightly more dramatic variation on the LSTM is gated recurrence unit. The next one is GRU. So this is Coethal. It is being introduced by Coethal. It combines the forget gate and input gate into a single update gate. Okay, and it also merges the cell state and the hidden state. Right, previously there was cell state. Right, so now this is being merged and it makes some other changes. So the resulting model is simpler than standard LSTM models. Right, so there are few of the most notable LSTM variants like depth-gated RNNs, and also there are many other models actually. So like if anybody asks you that which is being the best, do the differences matter? It is basically the comparison of popular variants. So it is finding that they are almost about the same, right? So this is how it is being, it is being worked. So LSTMs are a big step in what we can accomplish with RNNs. It is natural to wonder, is there another big step? So common opinion among researchers is there is a next step and it is attention, right? So the idea is to let every step of RNN pick information to look at from some larger collection of information. So if you are using RNN to create a caption describing an image, it might pick a part of the image to look for every word it outputs. Right, so attention is not only the exciting thread in RNN research, right? So work using RNN's generative models also is very interesting, right? So I hope this is really helpful for you to understand about LSTM and its variants, right? So let us meet in the next session. So here in this video, we have discussed about LSTM and its variants. I hope it is very clear to you.